Welcome back to this course on advanced memory hierarchy design. In this and the next lesson, I will discuss how virtual to physical memory address translation can be avoided during cache lookup. This requires knowledge of virtual memory, and I will provide a quick review in this lesson. The source of this lesson is sections B3 and B4 of the textbook by Hennessy and Patterson. First, let's quickly review why virtual memory is needed. Especially in the old days, programs were too large to fit in physical memory. A program needed, for example, 1 megabyte of memory, but the physical memory size was only 64 kilobytes. Now server processors have several gigabytes of main memory, so a single program may fit, but computers execute several processes at the same time, and the physical memory size is still smaller than the total size of all these processes. So there must be a way to share the physical memory between several processes running at the same time. The solution to this challenge is called virtual memory. The basic idea is to use main memory as a cache for secondary storage, typically a disk. This can work because typically at any time a process uses only a small fraction of the memory it needs. This implies, however, that there must be a way to translate virtual memory addresses, the addresses generated by the CPU, to physical memory addresses that are used to access memory. The mapping of virtual to physical memory roughly works as follows. Each process runs in its own virtual address space. This virtual memory is divided into pages, as illustrated here on the left. In this figure, I assume that the page size is 4 kilobytes, which is a typical page size. Physical memory, shown in the middle, is also divided into fixed size pages, and the mapping illustrated here indicates that virtual page 0 is mapped onto physical memory page 4, virtual page 1 to physical page 6, and virtual page 2 to physical page 1. Virtual page 3, on the other hand, is stored on disk. Virtual to physical address translation works as follows. As noted before, the virtual address space is divided into fixed size blocks called pages. Physical memory is also divided into blocks of the same size, and these blocks are called frames, but sometimes also physical memory pages. Then there is a page table, a table that is managed by the operating system that maps virtual pages to physical frames or pages. This table is called the page table. Because virtual and physical memory are divided into pages and the page size is a power of 2, any address can be divided into a page offset consisting of the least significant log base 2 page size bits and a page number. And the page table maps virtual page numbers to physical page numbers. This is illustrated in this figure. In this example, the page offset is 13 bits long, so the page size is 2 to the power of 13 or 8 kilobytes. Furthermore, virtual addresses are 64 bits long and physical addresses are 32 bits long. So the physical memory size is 2 to the power of 32, which equals 4 gigabytes. Finally, address translation means that the virtual page number is mapped onto a physical page number, and the physical page number concatenated with the page offset form the physical memory address. So the page table, which is managed by the operating system, maps virtual page numbers to physical page numbers. Each process, a process is simply a program that is being executed, has its own page table, and usually there is a special register called the page table register that points to the page table of the process that is currently being executed. This register can only be modified by the operating system. Page tables can be huge, several megabytes in size, and must also be stored in main memory. There are techniques that deal with this, such as dynamic sizing of page tables or multi-level page tables, but I will not discuss them. Let's look at an example page table. In this example, the virtual address space consists of 64 pages, page 0 to page 63. Then the page table might look like this. For every virtual page, there is an entry in the page table. Every entry consists of a valid bit and a frame number or physical page number. The valid bit indicates if the page is in main memory or not, and if not, it should be on disk. In this example, virtual page 1 is mapped onto physical page 2, or equivalently, but formulated the other way around, physical page 2 contains virtual page 1 and physical page 0 contains virtual page 3, as illustrated in this figure here on the right. When the access page is not in main memory, it's not called a page miss, but a page fault. This is because of historical reasons, but don't let it confuse you. If a page fault occurs, we need to retrieve the page from disk. Disks are very slow, about 100 times slower than main memory, so the miss penalty is huge. For this reason, pages are fairly large, typically 4 to 64 kilobyte. For the same reason, reducing the number of page faults is extremely important. The mapping of virtual to physical pages is, therefore, fully associative, and the least recently used replacement algorithm is worth to be implemented, even though its implementation is fairly expensive. Again, because page faults take a lot of time, they can be handled in software by the OS. In fact, when a page fault occurs, the operating system doesn't wait until the page fault has been handled, but schedules another process to run on the CPU. Finally, write-through is too expensive, so all virtual memory systems use write-back. Let me now illustrate the steps involved in a memory access. First, the CPU generates a virtual address. Then the hardware performs a lookup in the page table. Then it checks if the page is in physical memory. If it is, it can compute the physical address and access physical memory using the physical address, thereby completing the memory access. If the page is not in physical memory, then we have a page fault. Then control switches to the operating system, which will first load the page from disk, then it will update the page table, and finally the physical address can be computed and the memory access completed. Virtual memory paging means that every memory access now involves two memory accesses. One access to the page table to compute the physical address, and another memory access to actually get the data. But we know that memory accesses are slow, so this is disastrous. What can we do about it? The solution is to exploit the locality of reference to the page table. If a page has been accessed and a virtual page number has been translated to a physical page number, then it is very likely that the page will be accessed again very soon, and the same translation has to occur. To exploit this locality, all modern processors have a special hardware cache that contains recent virtual to physical page number translation. Unfortunately, this cache is not called a cache, but a translation Lookaside buffer. This figure shows a high-level block diagram of an Intel processor. In my opinion, it doesn't show a lot, but what can be seen is that it has an instruction translation Lookaside buffer, ITLB, the yellow block immediately under the orange block labeled branch prediction at the top. The TLB is organized as a cache, but is slightly different from a normal cache. Every TLB entry has a valid and a dirty bit. The valid bit indicates if the entry is valid or not, just as in a normal cache. The dirty bit, however, does not indicate that the entry has been written, but that the page has been written and therefore needs to be written back to disk when it is replaced. Every TLB entry also has a tag to determine if the access page is present in the TLB. Actually, not the access page is present in the TLB, but its physical page number. Then every TLB entry has a data field corresponding to the physical page number. And finally, there are some other bits related to protection and recency of access. For example, if a page is read-only, then this is indicated in the protection bits, and an exception will be generated if the CPU tries to write that page. Because at any time a process uses only a few pages, TLBs are usually small. The typical size is 8 to 128 entries. Finally, TLBs are often fully associative, and the tags of all entries are compared to the tag of the access page in parallel. A fully associative memory structure is often also called a content addressable memory, since no address or index is used to locate the data, but parts of its contents, in this case the tag. This figure shows the organization of the data TLB of the AMD Opteron processor. The virtual address is 36 plus 12 equals 48 bits long. The page offset is 12-bit, so the page size is 2 to the power of 12 or 4 kilobyte. The remaining 36 bits are the virtual page number. The TLB has 40 entries and is fully associative, so all entries are checked in parallel for a tag match. 40 entries? That's an odd number. Well, while many cache parameters have to be a power of 2 for fast access, the associativity doesn't have to be a power of 2. Apparently, the AMD designers had room left on the chip for a 40-entry TLB. Each TLB entry consists of several fields. The valid bit indicates if the TLB entry is valid or not. The RW bit says if the page is read-only or read-write. The US bit indicates if a user can access the page or only the supervisor, meaning the operating system. The dirty bit says if the page has been modified. The accessed bit indicates if the page has been read or written since the bit was last cleared. This is used to implement LRU. And the 36-bit tag field contains the virtual page number. Since the TLB is fully associative, no bits from the virtual page number can be ignored. There will be a TLB hit if the tag matches the virtual page number of the access page. In this example, it is assumed that the third entry hits as indicated by the vivid blue color. The last field is the physical page number. This 28-bit number is concatenated with the 12-bit offset to obtain the 40-bit physical address. Finally, this 40:1 multiplexer selects the physical page number whose tag matches the virtual page number of the access page. This completes this lesson. Thanks for watching. Now we have everything in place to describe how virtual to physical memory address translation can be avoided during cache access, and I will do so in the next lesson. Hope to see you back.